Tonight, we're going to explore one of the most compelling cosmic rivalries of the 21st century. For nearly 50 years, the silver globe hanging in the night sky seemed like a closed chapter of history. We arrived, planted flags, gathered a few samples of grey dust, and came home, leaving the moon in absolute undisturbed peace. But the Eastern Giant has shattered that silence. Driven by an extraordinary economic and technological surge, China is lifting its eyes toward the stars with an unyielding ambition. Their objective is clear. This is no longer about mere political vanity or temporary expeditions. It is about permanent settlement and exploiting the massive unprecedented benefits of a new frontier. We have been drawn into a fierce modern race for the high ground. Stay with us, and by the end of tonight, you will fully understand exactly why so many nations are rushing back to the silver dust and whether we are quietly falling behind China in this grand cosmic contest. Before we dive in, if you share our passion for drifting through the cosmos, please take a moment to like this video or subscribe. It's a small gesture, but it goes a long way in helping this channel connect with more inquisitive souls like yourself. Now let the journey unfold. In the quiet chill of October 1957, the evening sky over the Western world changed forever. It was not a change you could see with the naked eye, but rather one you felt in the sudden, heavy silence of the night. Then came the sound, a rhythmic, hypnotic beep 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 broadcast to the world by a polished metal sphere no larger than a beach ball. Sputnik 1 had arrived. Traveling along an elliptical low Earth orbit, a curved path just above our atmosphere, where gravity and momentum hang in a delicate, endless balance, this solitary Soviet beacon shattered the illusion of Western technological invulnerability. For the generation watching the stars from their backyards, the psychological blow was profound. The skies, once a canvas of peaceful wonder, suddenly felt occupied. In Washington, the political establishment collapsed into a state of quiet panic, an existential dread, known to history as the Sputnik shock. The equation was simple and terrifying for politicians of the era. If the Soviet Union possessed a rocket powerful enough to slip a satellite into the heavens, they possessed the power to deliver a thermonuclear warhead to any city in North America within minutes. The high ground had been taken, and the West was looking up from the valley. Before the dust of that initial shock could settle, the spring of 1961 brought an even heavier silence. In April of that year, a young Soviet pilot named Yuri Gagarin climbed into a cramped capsule called Vostok 1. With a single word, Poyachali, meaning let's go, he was propelled into the ink-black void, achieving orbital velocity, the blinding speed of 17,500 miles per hour required to perpetually fall around the Earth without ever hitting the ground. For 108 minutes, a single human being looked down on our blue planet, completely detached from the geopolitical borders below. For Western leaders, Gagarin's voyage was the ultimate validation of their deepest fears. It felt as though the future itself was being written in Cyrillic. The public psychological landscape shifted from mere anxiety to an urgent demand for action. This second defeat forced the hand of a young president, John F. Kennedy. It was no longer a matter of scientific curiosity. It was a race for survival, a test of which civilization had the stamina to claim the cosmic frontier. Driven by the memory of those early setbacks, the United States spent the decade of the 1960s transforming itself into an industrial and scientific titan. It was an era where the steady hum of slide rules and the smell of machine oil filled vast engineering floors across the nation. Before the grand voyage could begin, America had to learn how to survive in the deep void. Through the solitary flights of Project Mercury and the two-man operations of Project Gemini, astronauts practiced the delicate art of orbital rendezvous, the complex ballet of matching the speed and direction of two separate spacecraft so they could gently link up in the silence of space. They stepped out into the vacuum, tethered only by thin silver cords, learning how the human body behaves when weightless. All of these hard-won lessons converged into a single, towering monument of human ingenuity, the Saturn V rocket. Standing over 360 feet tall, it was a cathedral of aluminum and steel, consuming 15 tons of fuel every single second. At its base sat 5 massive F1 engines, which utilized gimbaled thrust, a sophisticated method of swiveling the roaring exhaust nozzles to steer the giant vehicle, much like a sailor moving the rudder of a great ship in a heavy sea. When this mechanical behemoth roared to life on the launch pads of Florida, it did not merely fly. It shook the very ground, generating a low-frequency rumble that could be felt in the chest miles away. The ultimate goal of this masterpiece was to help a fragile crew achieve escape velocity, the absolute mind-bending speed of 25,000 miles per hour needed to tear completely free from the invisible heavy chains of Earth's gravity. Once cleared of our blue planet, the spacecraft had to perform a maneuver known as trans-lunar injection. This was the perfectly timed, solitary firing of the rocket's third-stage engine that nudges a spacecraft out of its comfortable orbit around our world and sends it coasting across a dark, silent ocean toward the silver shore of the moon. For 3 quiet days, the men of Apollo traveled through a stillness so profound it is difficult for our earthbound minds to comprehend. Then came July 1969. The entire world seemed to hold its collective breath as the lunar module named Eagle detached from the command ship and began its perilous descent toward the lunar surface. The pilots, Neil Armstrong and Buzz Aldrin, flew down toward an ancient, untouched landscape called Mare Tranquillitatis, or the Sea of Tranquility. As the thin lunar dust billowed outward in the vacuum, the engines relied on hypergolic propellants, special volatile chemicals that burst into furious life the very instant they touch one another, requiring no spark plugs or complex ignition systems to work. It was a design chosen for its absolute reliability, because out there, 240,000 miles from home, there was no room for error. When the blue exhaust faded, Armstrong's voice crackled across the void, calm and steady, announcing that the Eagle had landed. Hours later, he stepped onto the powdery, charcoal-gray dust of the moon. His boots pressed into a soil that had remained undisturbed for 4 billion years, moving effortlessly in a world with only 1/6 of Earth's gravity, a gentle, dreamlike state, where every stride feels like floating through water. For a brief, shining moment in the summer of 1969, the geopolitical anxieties of the Cold War dissolved into a sense of unified, transcendent wonder. Humanity had broken its earthly bonds and touched the face of the heavens. In December of 1972, the brilliant flame of the Apollo era quietly flickered out, and a long winter night fell upon deep space exploration. When the final crew of Apollo 17 departed the gray lunar plains, leaving their lonely bootprints in the fine regolith, the thick blanket of powdery stone and cosmic stardust that covers the airless surface, humanity pulled back into its comfortable home. For more than 50 years, the United States a nation that had successfully engineered the most complex voyage in human history, chose to leave the silver world in total solitude. The sudden halt of this grand adventure was driven by cold, earthly realities rather than a lack of wonder. The primary engine of the program had always been geopolitical survival. Once the ultimate political trophy had been won and the American flag was firmly planted, the intense existential pressure of the Cold War dissolved. The immense federal budget, which had once consumed more than 4% of the American national treasury, dwindled almost overnight to less than half of 1%. Congress viewed the moon as a mission completed, a glorious but deeply expensive monument that could no longer be sustained amidst pressing economic concerns back on the ground. NASA was forced to abandon its reliance on an expendable launch architecture, a technical phrase for massive rockets and hardware that are used only once and then discarded into the ocean, making every single flight an incredibly expensive luxury. To find a more sustainable path, the strategic focus shifted entirely to low Earth orbit, the narrow, peaceful band of space just a few hundred miles above our heads. For decades, America poured its brilliant minds into the Space Shuttle program and the construction of the International Space Station, choosing to master the art of living in close proximity to home rather than taking giant, costly leaps into the deep dark. Another silent destroyer of the lunar dream was the shifting tide of Washington politics. A journey to the moon requires decades of unwavering dedication, yet the American presidency operates on short cycles of 4 or 8 years. This created a frustrating cycle of political inertia, the tendency of a massive bureaucratic system to keep moving in one direction until a new leader abruptly forces it to stop. One administration would announce a grand return to the moon only for the next to cancel the project due to changing financial priorities. Millions of hours of engineering designs were routinely shelved, forcing NASA to repeatedly tear down its foundations and start anew. Over the decades, the specialized factories that forged the mighty Saturn rocket closed and the unique tools were dismantled. More importantly, the generational know-how, the practical unwritten wisdom held by the master machinists and engineers who knew exactly how to weld those roaring engines, slowly faded away as that brilliant generation entered their quiet retirement years. The delicate industrial ecosystem had ceased to exist, leaving the Gray Plains to sleep undisturbed. While America's eyes were turned closer to home, a new titan was quietly stirring in the East. Fueled by decades of staggering economic growth and rapid technological breakthroughs, China began to lift its gaze toward the silver horizons of the night sky. They named their grand lunar ambition after Chang'e, the ancient goddess of the moon, signaling the awakening of a disciplined giant ready to claim its place among the stars. The rise of China's modern space program was not marked by a sudden chaotic sprint born of political panic, but rather by a deeply patient, step-by-step philosophy known to engineers as an incremental development strategy. For a generation of Western onlookers who well remembered the breathless, frantic races of the mid-20th century, this quiet discipline felt profoundly different. It was a philosophy that rejected the shifting winds of short-term political cycles, choosing instead to map out a multi-decade journey with the steady, unyielding precision of an automated assembly line. This grand strategy was designed to roll out in distinct logical waves, ensuring that every piece of hardware and every line of computer code was proven flawless before the next step was ever attempted. The opening chapter of this great undertaking known simply as Phase 1, focused entirely on a singular foundational goal: mastering the cold, silent environment of lunar orbit. The journey began in the late autumn of 2007 with the launch of Chang'e 1, followed 3 years later in the month of October 2010 by her more advanced sister ship, Chang'e 2. The mission parameters for these twin orbiters were clear. They were to bridge the vast void between worlds and construct a flawless digital blueprint of the Moon. To achieve this, the spacecraft relied on a Hohmann transfer orbit, an elegant, highly calculated flight path that uses precisely timed engine burns to coast along a curved trajectory from one planetary body to another, using the absolute minimum amount of fuel. Once they arrived in the deep dark of the lunar neighborhood, they settled into a steady polar orbit, sliding gracefully from north to south over the rotating silver globe. To see through the ancient shadows, they carried charge-coupled device stereo cameras, highly sensitive electronic eyes capable of capturing multi-dimensional, stereoscopic images of the alien terrain. Working alongside these cameras were sophisticated laser altimeters, which are specialized scientific instruments that bounce high-speed beams of light off the ground to measure the exact height of lunar mountains and the precise depth of hidden craters. The results of this initial phase were a masterpiece of celestial cartography. China produced a complete, uninterrupted three-dimensional map of the entire Moon, mapping safe havens for future missions and discovering subtle gravity anomalies that had remained hidden from human eyes for generations. With the lunar geography thoroughly mastered, the incremental philosophy naturally advanced to its second major milestone, the soft landing. In December of 2013, the world watched in quiet fascination as the Chang'e 3 spacecraft began its perilous, automated descent toward the dusty plains below. This mission showcased a remarkable feat of modern engineering, known as an autonomous hazard avoidance system, a sophisticated onboard computer brain that scans the ground below in real time during the final seconds of flight, automatically identifying dangerous boulders or treacherous slopes and steering the craft to a flat, safe patch of ground without any human intervention from Earth. The descent was a flawless success, marking the first time a human spacecraft had gently touched down on the Moon in nearly 40 years. The lander settled quietly into a vast, dark volcanic plain known as Mare Imbrium, or the Sea of Rains. From the belly of the dormant lander rolled a small, six-wheeled companion named U2, or the Jade Rabbit. Equipped with a lunar-penetrating radar, a device that shoots high-frequency radio waves deep into the soil to see what lies hidden beneath the surface. This small rover discovered that the lunar crust was far more complex than previously believed, revealing distinct layers of ancient solidified volcanic lava that spoke of a volatile past. Phase 1 had proven to the world that this patient industrial approach was a formidable force. They had mapped the wilderness, mastered the soft landing, and left their first mechanical tracks in the ancient dust. As the clock of human history ticked into the late 2000s, the architects of the Chinese space program prepared to attempt what the rest of the world had long deemed too perilous, too complex, and perhaps even unnecessary. Their target was a realm shrouded in both literal and metaphorical shadow, the far side of the Moon. For centuries, humanity had looked up at the same familiar silver face, an artifact of a celestial phenomenon known as tidal locking. This is a profound astrophysical mechanism where the gravitational grip of a massive planet slows down the rotation of its satellite over billions of years until the Moon rotates on its own axis at the exact same speed it orbits the parent world. The result is an eternal asymmetry. One half of the moon is permanently turned toward our backyards, while the other half remains forever turned away, staring out into the velvet void of deep space. To land a spacecraft on this hidden hemisphere was a challenge of terrifying proportions. The primary obstacle was not the rugged crater-scarred terrain, but the absolute laws of physics. Because the moon is 250,000 miles of solid heavy rock, it acts as an impenetrable barrier to radio waves. The moment a spacecraft slips behind the lunar horizon, it enters a zone of total electromagnetic silence. Direct communication with Earth becomes completely impossible, meaning a landing crew or an automated probe would be utterly blind and deaf, cut off from the engineers in the control room. To pierce this wall of silence, China had to construct an entirely new kind of celestial infrastructure. In the spring of 2018, they launched the unsung hero of this grand epic, a relay satellite named Queqiao-1, or the Magpie Bridge. The satellite was sent into a highly specialized orbit around the Earth-Moon Lagrange Point 2. To the layman, a Lagrange point can be understood as a cosmic parking spot, a precise location in deep space, where the competing gravitational pulls of two large bodies like the Earth and the Moon balance out perfectly with the centrifugal force of a smaller object. It is a quiet gravitational eddy where a spacecraft can hover with minimal fuel like a ship anchored in a calm harbor. Positioned at this unique vantage point beyond the Moon, Queqiao-1 could maintain a clear, uninterrupted line of sight with both the hidden far side below and the tracking stations back on Earth acting as an immortal bridge for human commands and whispered data. With the communications lifelines securely established, the stage was set for the main act. In December of 2018, a massive Long March 3B rocket roared to life at the Xichang Satellite Launch Center. This workhorse of the Chinese fleet, an industrial monument of steel and liquid propellant, lifted the Chang'e 4 spacecraft out of Earth's heavy embrace and sent it coasting silently across the dark ocean of space. The destination was the von Karman crater, a monstrously deep and ancient impact basin near the lunar South Pole, a place where the crust of the Moon had been torn open billions of years ago by a cataclysmic asteroid collision. On the 3rd of January 2019, the world held its breath as Chang'e 4 approached its final descent. Because of the vast distance, the onboard computers had to take total control, executing an automated landing down the steep, treacherous walls of the crater. The spacecraft utilized its laser rangers and thrusters to perform a vertical descent, hovering briefly to choose a flat patch of dust before gently settling into the gray wilderness. For the first time in human history, a mechanical ambassador from Earth had touched the pristine, unmapped surface of the lunar far side. The results of this historic triumph were nothing short of revolutionary. From the belly of the lander, a small silver-wheeled rover named Yutu-2 crept out into the dust, leaving the very first tracks on a world that had never seen a shadow from Earth. This tiny explorer was equipped with instruments for low-frequency radio astronomy, a scientific method of listening to the faintest, oldest whispers of the early universe. Because the far side of the Moon is permanently shielded from the deafening electronic chatter of human civilizations, our television towers, cellular networks, and radio stations, it is the quietest electromagnetic sanctuary in the solar system. Free from this noise, Chang'e 4 could look back into the cosmic dawn, capturing signals from the time before the very first stars were born. Furthermore, the rover's deep penetrating radar revealed the complex subterranean architecture of the far side, showing layers of coarse volcanic ejecta, the debris hurled outward by ancient cosmic impacts, proving that the hidden side of the moon had a vastly different and more violent history than the smoother plains of the side we see from our windows. U-22 would go on to break all longevity records, surviving for years in an environment that swings from blistering heat to a freezing dark of -180 degrees. With the lunar wilderness thoroughly mapped and the delicate art of the automated soft landing mastered, the patient engineers of the Eastern Titan turned their sights toward the ultimate prize of robotic exploration: sample return. It was no longer enough to merely look at the moon through electronic eyes or to scratch its surface with small mechanical wheels. The time had come to reach out across the 250,000-mile void, gather the ancient soil, and bring it safely home to Earth. This grand ambition formed the third and most technologically punishing phase of the lunar program, executed through the twin historic voyages of Chang'e 5 and Chang'e 6. For a generation of onlookers who had not seen fresh lunar materials returned since the 1970s, these missions represented a profound revival of cosmic geology, carried out with a level of automated precision that seemed to belong to the deep future. The first movement of this epic began in the late autumn of 2020 with the launch of the Chang'e 5 spacecraft. The target was a vast dark plain on the familiar near side of the moon, known as Oceanus Procellarum, or the Ocean of Storms, specifically near a massive volcanic monument called Mons Rumker. This site was chosen with immense scientific intent. While the American Apollo missions had sampled ancient highlands, China sought the youngest volcanic plains on the moon. To harvest these treasures, the spacecraft utilized a highly sophisticated sample return architecture, a complex modular system where a lander, an ascender, an orbiter, and a return capsule must all work in a flawless multi-stage choreography across deep space. Once on the surface, the lander deployed a robotic arm to scoop up surface dust and a diamond-tipped drill to extract a cylinder of pristine subterranean soil from a depth of nearly 6 feet. The true test of engineering came after the harvest. The ascender module had to use the flat top of the lander as a makeshift launch pad, firing its engines in the vacuum to blast itself off the moon and enter lunar orbit. There, it had to perform an automated robotic rendezvous and docking a blind mechanical handshake in the pitch-black void where two spacecraft traveling at thousands of miles per hour must find each other and lock together with millimeter precision. Once the precious cargo was transferred to the return capsule, the spacecraft journeyed back to Earth, culminating in a spectacular skip re-entry. This is a brilliant aerodynamic maneuver where the capsule hits the upper edge of Earth's atmosphere and bounces back out into space, briefly, much like a flat stone, skipped across the surface of a still pond, using the friction of the air to safely shed its tremendous cosmic speed before deploying its parachutes over the snowy plains of Inner Mongolia. In December of 2020, Chang'e 5 successfully delivered nearly 2 kilograms of pristine lunar soil to the waiting hands of scientists. The value of these samples was revolutionary. Laboratory analysis revealed that these basaltic rocks were only 2 billion years old, meaning the moon was volcanically alive and warm inside for 1 billion years longer than previously believed, completely rewriting the timeline of planetary cooling. Yet this was merely a prelude to an even more daring feat. In May of 2024, the program launched Chang'e 6, aiming for a destination that had never been touched by a sample return mission, the hidden far side of the Moon. The landing site was the immense South Pole Aitken Basin, specifically within the ancient rugged impact crater known as Apollo. Because this region is permanently turned away from Earth, the entire mission depended on the invisible lifeline of the Helium-2 relay satellite hovering quietly in its distant gravitational orbit to pass commands through the solid rock of the Moon. The difficulty of Chang'e 6 cannot be overstated. The far side is notoriously rugged, thick-crusted, and completely blind to direct human control. The spacecraft had to execute its drilling and scooping operations in a race against time, relying entirely on autonomous programming. In June of 2024, after a nail-biting journey, the return capsule touched down safely on Earth, carrying the world's very first samples from the mysterious far side of the Moon. The scientific value of the Chang'e 6 cargo is priceless. These ancient dark rocks plucked from the deepest scar in the lunar crust offer humanity a direct window into the violent infancy of the solar system more than 4 billion years ago. By comparing these materials to the younger soil of Chang'e 5, scientists are beginning to solve the grand riddle of lunar asymmetry, why the near side is covered in smooth, dark volcanic seas, while the far side is a rugged, battered wilderness of white mountains. As the midsummer warmth of 2026 wraps the world in a quiet embrace, the gaze of the scientific community is once again drawn away from our busy streets and lifted toward the silver light of the night sky. We find ourselves living through a historic pivot point, a moment where the long-laid plans of a distant empire are transitioning from blueprints into roaring reality. The curtain is about to rise on Chang'e 7, a mission that represents the most complex, daring, and technologically punishing robotic expedition ever sent into the deep dark of space. This is not merely another step in a sequence, it is a profound assault on the unknown, designed to unlock the secrets of the lunar South Pole and pave the way for permanent human habitation among the stars. The tactical timeline for this grand epic has been unfolding with the quiet, unyielding rhythm of an automated clockwork system. Earlier this year, in the quiet spring month of April 2026, the heavy components of the Chang'e 7 spacecraft were carefully transported to the coastal launch facilities of Wenchang. Now, as we enter the final 6 months of 2026, the tension in the control rooms is palpable, yet calm. The launch window is rapidly approaching a precise alignment of celestial bodies when a massive Long March 5 heavy-lift rocket, an industrial titan of liquid oxygen and hydrogen fuel, will roar into the heavens. This colossal vehicle, the undisputed workhorse of the Eastern Fleet, will carry a massive payload weighing several tons, hurling it out of Earth's heavy grip and sending it coasting across the quarter-million-mile dark ocean toward its treacherous destination. The chosen landing zone for this mission is a place of extreme geographical contrast, the rim of the Shackleton crater situated at the absolute bottom of the lunar globe. To understand why this rugged, inhospitable wilderness was chosen, one must understand the unique physics of the lunar South Pole. Because the Moon sits almost perfectly upright relative to the Sun, the sunlight at the poles strikes the ground at a razor-thin angle, skimming across the mountain tops, but never reaching the floors of the deepest valleys. This creates two distinct phenomena: peaks of eternal light, elevated ridges, that are bathed in near-perpetual sunshine, offering an endless supply of solar power, and permanently shadowed regions, those dark, sunless abysses where the temperature has remained at a freezing -230 degrees Celsius for billions of years. It is within these eternal shadows that scientists believe billions of tons of water ice are frozen in the dust, a priceless cosmic resource that can be melted for drinking water, split into oxygen for breathing, or refined into hydrogen for rocket fuel. The difficulty of landing and operating a spacecraft in this landscape is terrifying to contemplate. The South Pole is not a smooth volcanic plain like the sites chosen during the Apollo era. It is a chaotic vertical wilderness of towering cliffs, razor-sharp crater rims, and deep, pitch-black valleys. To survive, the mission relies on an intricate multi-vehicle choreography consisting of an orbiter, a lander, an advanced rover, and a specialized flying probe. This complex fleet must operate in an environment where a single miscalculation of a few feet could plunge a vehicle into a dark, freezing canyon where its solar panels would die instantly. Furthermore, because the high mountains of the pole frequently block direct radio lines to our planet, the entire architecture depends on an invisible, immortal lifeline in the sky, the Chang'e-2 relay satellite. Launched in the early months of 2024, this highly specialized spacecraft hovers in an eccentric frozen orbit, a beautifully calculated elliptical path that allows it to maintain a constant, high-speed data connection with both the hidden, shadowed valleys below and the tracking stations back on Earth. Without this mechanical guardian passing whispers of data through the vacuum, the entire expedition would be struck blind and deaf. The primary objective of Chang'e 7 is nothing less than a revolutionary hunt for cryogenic volatiles, frozen chemical compounds that evaporate instantly when exposed to heat, with water ice being the ultimate prize. To achieve this, the mission will deploy its most fascinating mechanical ambassador, a miniature flying probe known to engineers as the Hopper. This small, spider-like vehicle is equipped with its own independent rocket propulsion system. After the main lander touches down on a sunlit ridge, the Hopper will detach fire its engines and gracefully fly off the ground, leaping directly over the edge of the cliffs and descending into the pitch-black, freezing depths of the permanently shadowed craters. Operating completely in the dark, guided by artificial intelligence, the Hopper will use a mechanical drill to pierce the icy crust, gathering samples and analyzing them. With an onboard molecular mass spectrometer, a highly advanced tool that vaporizes materials with heat, to read their chemical signatures like a fingerprint. It will then fire its thrusters once more, leaping back out of the darkness and returning to the sunlit heights to recharge its batteries and broadcast its revolutionary findings back home. Working alongside the Hopper will be a heavily armored AI-driven rover equipped with a lunar penetrating radar, capable of mapping the layers of ice and stone up to 100 feet beneath the surface. Together, these machines will create the first comprehensive resource map of the lunar South Pole, transforming a cold, alien desert into an identifiable piece of real estate, ready for the arrival of the first human construction crews before the end of the decade. Yet as the great eastern giant settles into its steady, unyielding stride, it does not hold a monopoly on the silver horizons. Across the oceans, other independent nations are quietly igniting their own engines, from the cost-efficient brilliance of New Delhi to the masterfully precise laboratories of Tokyo. A new fleet of cosmic pioneers is rising, proving that this grand journey is no longer a game played only by superpowers. In the grand ledger of modern space exploration, There exists an unspoken assumption that to touch the stars, a nation must possess a blank check, a bottomless treasury, capable of absorbing billions of dollars in development costs. Yet far away from the massive budgets of Washington and Beijing, a quiet, brilliant contrarian was rewiring the rules of the cosmos. The Indian Space Research Organization, known affectionately to engineers around the globe as ISRO, did not approach the moon with the brute financial force of a traditional superpower. Instead, they relied on a philosophy of elegant minimalism, a masterclass in frugal engineering that proved a nation could conquer the cosmic frontier through sheer intellectual stamina and mathematical precision. For a generation of Western onlookers who grew up watching the multi-billion-dollar epics of the 20th century, India's approach was a revelation, a demonstration that a spacecraft could be sent to the lunar wilderness for less than the cost of producing a single summer blockbuster movie in Hollywood. The opening notes of this financial and engineering miracle resonated across the world on the 14th of July, 2023. On that bright afternoon, at the Satish Dhawan Space Center, on the coast of the Indian Ocean, a massive launch vehicle stood gleaming against the sky. This was the Launch Vehicle Mark III, an industrial workhorse built with a rugged, no-nonsense architecture that relied on solid booster rockets and a liquid-fueled core. This mighty machine was tasked with carrying the Chandrayaan-3 spacecraft out into the void. The entire budget for this historic expedition was pinned at approximately $75 million, a figure so astonishingly lean that it caught the attention of every bean counter and aerospace auditor on Earth. To achieve this, Indian mathematicians had to abandon the luxury of a direct, high-powered flight path. Instead, they turned to the ancient laws of orbital mechanics, the delicate branch of physics that dictates how objects move through space under the influence of gravity. Instead of blasting straight toward the moon, Chandrayaan-3 spent weeks performing a series of precisely timed orbit-raising maneuvers. This is a highly efficient navigation technique where a spacecraft enters an elongated path around Earth, firing its small engines only at the perigee, the exact point in the orbit where the craft is closest to the planet and moving at its maximum speed. By zapping the engines at this sweet spot, the spacecraft uses the Earth's own rotational energy to stretch its flight path further and further outward, like a child on a swing, pumping their legs at the lowest point to go higher. It was a patient, slow-motion journey that took over a month, but it saved millions of dollars in precious fuel, allowing a modest rocket to punch far above its weight class. By mid-August, the moon's gravitational embrace caught the spacecraft, and the focus shifted to the ultimate destination, the uncharted southern polar region, specifically near the 69 degrees south latitude line. No nation in history had ever attempted to land a vehicle so far down the freezing spine of the lunar globe. The site was chosen because it sits at the threshold of the forbidden territory, where billions of tons of ancient water ice are believed to be trapped in eternal darkness. For scientists, this region is a pristine, untouched museum of the early solar system, a place where the pristine soil has never been cooked by the harsh rays of the sun or disturbed by previous human machinery. The climax of this epic unfolded on the 23rd of August, 2023. In control rooms across India, a heavy, reverent silence fell as the spacecraft entered the final 15 minutes of its descent, a period known to engineers as the 15 minutes of terror. Because the distance between worlds creates a communication lag of several seconds, human pilots cannot steer the craft in real time. The onboard computers had to take absolute command, executing a complex series of automated braking maneuvers to shed thousands of miles of speed. The lander, named Vikram or Valor, utilized 4 throttling engines to gently slow its descent, using its laser altimeters to measure the dropping distance and its hazard detection cameras to scan the gray wilderness below for deadly boulders. With a whisper of dust in the vacuum, Vikram touched down flawlessly on the gray, primeval plains. India had officially become the 4th nation on Earth to achieve a soft landing on the Moon, and the first ever to plant its mechanical feet near the elusive South Pole. Within hours of the landing, a small 26-kilogram rover named Pragyan, meaning wisdom, rolled down a golden ramp and took its first slow steps into the fine lunar dust. Operating on just a fraction of the power required to run a standard household microwave, this tiny 6-wheeled explorer began an extraordinary scientific harvest. Pragyan was equipped with a laser-induced breakdown spectroscopy instrument, an advanced scientific tool that shoots a high-powered invisible laser beam directly at a rock, vaporizing a microscopic speck of the stone into a glowing puff of plasma, then reading the light signature of that flash to determine exactly what chemical elements are hidden inside. Through this technique, the rover discovered a surprising and Dao presence of sulfur in the polar soil, an element that indicates a rich history of ancient volcanic activity. It also confirmed the presence of aluminum, calcium, iron, chromium, and titanium, alongside a precious bounty of oxygen bound tightly within the mineral dust. The little rover Pragyan and its loyal mothership Vikram finished their work as the long, freezing 14-day lunar night crept across the South Pole, entering an eternal, peaceful slumber in the grey dust. They rest there now, silent monuments to human ingenuity, bathed in the cold light of 1,000,000 distant stars. In the quiet world of advanced engineering, there is a distinct reverence for the art of precision, the kind of mastery found in the delicate gears of a handmade watch or the seamless fit of ancient wooden architecture. When the nation of Japan turned its focus toward the silver horizons of the night sky, they did not seek to build the loudest or the largest machines in the cosmic arena. Instead, the Japan Aerospace Exploration Agency, known to the world as JAXA, chose to bring the spirit of the master craftsman to the lunar wilderness. They understood that the future of space exploration would not be won merely by burning mountains of fuel, but by guiding a spacecraft with the absolute pinpoint accuracy of a laser beam. Their grand experiment would challenge a fundamental rule of space travel, shifting humanity's capability from landing where it is easy to landing exactly where we want. This quiet revolution in celestial navigation manifested in a brilliant compact spacecraft named SLIM, an acronym for the Smart Lander for investigating the Moon. The journey began in the late summer month of September 2023, when a reliable Japanese H-2A rocket lifted the probe into the ink-black sky. For months, the tiny spacecraft coasted along a patient, energy-saving trajectory, quietly slipping into lunar orbit. The ultimate test arrived in the deep winter of the following year, on the 19th of January 2024. The chosen destination was a treacherous, unforgiving patch of grey terrain known as the Scioli crater. This specific site was located on the steep slope of an ancient impact mound, tilted at a precarious angle of 15 degrees. Geologists desperately wanted to reach this location to study the exposed olivine rocks, deep planetary materials, dredged up from the moon's hidden mantle during a cataclysmic asteroid collision billions of years ago, which could hold the secret to how our cosmic world was born. To descend safely onto the face of a steep hill required a technological leap known as vision-based navigation. In traditional space missions, a lander dropped blindly onto a massive flat plane, relying on simple radar to measure height, leaving a margin of error that spanned several miles. JAXA rejected this limitation. They equipped SLIM with sophisticated real-time crater matching algorithms, essentially an advanced computer brain that takes high-speed photographs of the ground during the descent and instantly compares them to a pre-loaded digital map of the lunar topography. This process operates exactly like modern facial recognition software on a smartphone. As the spacecraft falls through the vacuum, it recognizes the unique shapes of individual craters, just as a human brain recognizes a familiar face or a distinct street corner. This allowed the onboard computers to calculate the craft's exact position with astonishing speed, adjusting its thrusters second by second to guide it toward its tiny target. The physical act of touching down on a 15-degree slope required a radical rethink of landing gear design. Traditional heavy legs would cause a spacecraft to tip backward and roll down the mountain. To solve this, Japanese engineers created an innovative main landing gear made of printed aluminum lattice structures, three-dimensional sponge-like metal bumpers, designed to intentionally crush and deform upon impact, absorbing the violent kinetic energy of the landing like a high-tech car bumper in a slow-motion collision. On that historic night in January 2024, the automated choreography worked with stunning success. Despite a minor engine anomaly during the final moments, SLIM touched down precisely 55 meters from its absolute target, shattering the old standard, and achieving the world's very first pinpoint landing with a margin of error well under 100 meters. With this triumph, Japan officially became the fifth nation in human history to achieve a soft landing on the moon. This masterclass in precision engineering has earned Japan a vital, unshakable position in the American-led Artemis Alliance, the great international coalition aimed at returning humans to the deep dark of space. Rather than attempting a solitary, massively expensive lunar campaign, JAXA has partnered with NASA to provide a critical piece of infrastructure, a pressurized lunar rover. To the layman, this can be understood as a magnificent self-contained mobile home on wheels. Unlike the open rovers of the 1970s that required astronauts to wear clumsy, heavy spacesuits, this vehicle will feature an advanced life support system and a thick insulated cabin where a crew of 2 can live, sleep, and work in comfort for up to a month at a time, traveling hundreds of miles across the rugged polar wilderness. It is an extraordinary investment of Japanese industrial might, and the geopolitical trade for this technology is historic. In a formal agreement signed in Washington, the United States has pledged that a Japanese astronaut will be granted a coveted seat on a future Artemis mission, becoming the very first non-American human being to step onto the surface of the moon. As we watch the grand chessboard of the cosmos unfold, a quiet revolution is taking place far away from the massive bureaucratic empires of the traditional superpowers. A new breed of spacefarers has entered the arena, nimble, determined, and unburdened by old Cold War histories. These are the dark horses of the deep, dark nations, like South Korea, the United Arab Emirates, and Israel. They are rewriting the rules of engagement through a profound shift known as privatization, the transition from state-controlled space programs to a commercial marketplace where private companies sell transport services, much like cargo ships carrying freight across our earthly oceans. This new commercial landscape allows smaller nations to purchase a ticket for their specialized instruments to ride aboard private delivery vehicles traveling to the silver deserts of the moon. The most quietly formidable of these new competitors is South Korea. In the winter month of December 2022, the nation placed its very first ambassador into the lunar neighborhood, a magnificent spacecraft named Danuri, which translates beautifully to "enjoy the moon." Danuri settled into a pristine polar orbit, a flight path that circles the moon from top to bottom, allowing the craft to scan every inch of the turning globe below. While the spacecraft carries 5 advanced instruments forged by Korean scientists, its most strategically vital cargo is an ultra-sensitive eye provided by NASA known as the shadow cam. To the layman, the shadow cam can be understood as night vision goggles for the cosmos. It is a camera designed to capture high-resolution images using only the faintest starlight, reflecting off distant crater walls, peering directly into the permanently shadowed regions, those ancient freezing abysses at the lunar poles that have not seen a single ray of direct sunlight for billions of years. The data sent back by Danuri has become the absolute foundation for the American-led return to the moon, mapping the exact locations where water ice is hidden and helping NASA planners select the precise spots where human boots will step during the upcoming Artemis missions. Seoul is not content with being a passenger. They are actively developing their own next-generation launch vehicle with the grand ambition of landing an independent Korean rover on the surface by the year 2032. While South Korea represents the steady climb of state-backed engineering, the small nation of Israel demonstrated the raw grit of private initiative through an extraordinary organization called Space IL. In the spring of 2019, this non-profit group attempted what had always been the exclusive domain of global empires, launching a compact, budget-friendly lander named Bereshit, the Hebrew word for "in the beginning." Built on a shoestring budget, financed largely by private philanthropists, Bereshit traveled across the void, successfully executing a lunar orbit insertion, the delicate braking maneuver where a spacecraft slows down just enough to let the moon's gravity gently catch it instead of letting it fly past into the empty dark. The world watched in awe as this privately funded underdog approached the gray plains. Tragically, in the final minutes of the descent, a critical main engine failure caused the control rooms to lose contact, and Bereshit suffered a hard landing, a polite engineering phrase for a high-speed crash that destroys the vehicle upon impact. Though the spacecraft was lost, the mission transformed the global space industry forever, proving that a small group of private citizens could build a machine capable of reaching the moon. Today, the undeterred team is forging ahead with Bereshit 2, a daring twin-lander mission designed to finish what the Pioneer began. Further to the east across the desert sands, the United Arab Emirates has established its own unique footprint by treating space exploration as a high-tech venture capital investment. Rather than spending decades developing heavy industrial infrastructure, the Emirati space program excels at international collaboration and payload integration, the art of designing sophisticated scientific instruments and fitting them safely onto spacecraft built by global partners. In 2023, the nation deployed its first mechanical ambassador, the miniature four-wheeled Rashid rover, named in honor of the visionary leader who built modern Dubai. The tiny explorer was tucked into the belly of a private Japanese commercial lander. While that specific mission met a tragic end on the lunar slopes the Emirates did not waver. They immediately initiated the development of Rashid, leveraging their immense financial resources to secure new commercial launch contracts, proving that in the modern era, resilience and capital can bridge any technological gap. With the cosmic stage growing crowded with new players and private pioneers, a deeper question quietly emerges in the stillness of the night. Why now? Why this sudden 21st century rush back to a world we left behind for generations? The truth is, this is no longer a mere flag-planting vanity project. Beneath that cold grey dust lies the raw material of the next century: boundless energy, priceless wealth, and absolute geopolitical power. To the casual observer, looking out into the quiet of the night, the silver globe hanging in the velvet sky seems like a symbol of eternal stillness, a poetic watchman that has remained unchanged since the dawn of human memory. Yet beneath that cold grey dust lies a pragmatic reality that is quietly transforming the moon into the most valuable piece of real estate in the solar system. We are standing at the threshold of a modern energy frontier, a cosmic gold rush that mirrors the fierce oil booms and mineral rushes of our earthly history, but one that is unfolding in absolute majestic silence. The nations currently burning mountains of fuel to cross the Great Void are not driven by mere curiosity. They are hunting for two specific priceless treasures that could dictate the economic and political survival of human civilizations for centuries to come. The first of these treasures is an invisible, weightless bounty scattered across the sun-drenched plains, an exotic material known to theoretical physicists as Helium-3. On our home world, this substance is an extreme rarity, a microscopic byproduct of nuclear decay that is nearly impossible to harvest. Yet on the airless surface of the moon, it sits in staggering abundance, trapped within the top layers of the lunar soil. For billions of years, the sun has been exhaling a continuous stream of charged particles known as the solar wind. Because the Earth is shielded by a thick atmosphere and a powerful magnetic field, these particles are deflected away from us. But the moon possesses no such shield. It has sat unprotected for eons, allowing the solar wind to gently bake the lunar dust, embedding countless tons of Helium-3 directly into the grey Earth. To understand why a single ton of this material is worth billions of dollars, we must look into the grand holy grail of modern physics: nuclear fusion. For decades, our earthly power grids have relied on nuclear fission, the industrial process of splitting heavy, unstable atoms like uranium to release heat. While effective fission creates a heavy burden of toxic radioactive waste that remains dangerous for thousands of years. Nuclear fusion, however, is the exact opposite. It is the process of forcing light atoms to combine under immense heat and pressure, mimicking the exact engine that powers our sun and the brilliant stars. It is the ultimate source of clean power. If engineers can master fusion using Helium-3 as a fuel, a single suitcase full of this lunar material could power a major Western metropolis for an entire year. It produces absolutely no greenhouse gases, leaves behind zero radioactive waste, and carries no risk of a core meltdown. It is the promise of infinite clean energy independence, and the nation that controls the supply will hold the keys to the 21st century global economy. Yet while Helium-3 represents the magnificent promise of tomorrow's energy grid, there is another far more urgent resource hidden at the absolute bottom of the lunar globe. This is the treasure of lunar water ice locked away in the perpetual darkness of the South Pole. For generations, scientists believed the moon was a bone-dry desert, a world completely parched by the harsh rays of the sun. But modern satellites have revealed an extraordinary paradox. Because the moon sits perfectly upright relative to its path around the sun, the sunlight at the poles strikes the ground at a razor-thin horizontal angle. This means that while the high mountain ridges are bathed in near-perpetual sunshine, the floors of the deepest, steepest craters never see a single ray of light. These deep depressions are known to astronomers as permanently shadowed regions, eternal sunless abysses, where the temperature has remained at a freezing -230 degrees Celsius for more than 2 billion years. They are the coldest places in the known universe, acting as cosmic deep freezers. Over cosmic time, comets and water-bearing asteroids have slammed into the moon, vaporizing upon impact. While most of that moisture escaped into the empty void, a significant portion drifted into these freezing polar traps, instantly condensing and freezing into a hard, crystalline frost mixed with the lunar stone. The value of this ice is not merely for drinking water. To sustain a human colony, though that is vital, its true worth lies in its chemical components. Through a well-understood industrial process known as electrolysis, using an electrical current to snap the chemical bonds of a water molecule, future automated refineries can easily separate this ice into pure hydrogen and pure oxygen. Oxygen is the breath of life for any astronaut, but when liquefied and paired with liquid hydrogen, it becomes the most powerful, efficient rocket fuel known to chemical engineering. This transformation completely rewrites the economics of space travel, turning the moon into a cosmic gas station. Because Earth possesses a massive gravitational pull, launching a heavy rocket filled with fuel from our planet is an incredibly expensive, inefficient endeavor. Most of the vehicle's energy is wasted just trying to break free from our home world. But the moon's gravity is only 1/6 of what we feel beneath our boots today, and it has no atmosphere to cause friction. A spacecraft could lift off from the lunar surface using only a fraction of the energy required on Earth. By harvesting polar water ice and refining it into fuel right there on the lunar surface, humanity can launch massive deep space expeditions to Mars or the asteroid belt for a tiny fraction of the cost, opening the door to a true spacefaring civilization. In the quiet stillness of the late evening, as the world beneath our feet slows to a gentle rest, our minds can wander back to the grand sweeping histories of human frontiers. For centuries, the law of the land has been determined by lines drawn upon a map, forged by fences' treaties, and the steady presence of homesteaders. But as we lift our eyes to the silver shores of the moon in this 21st century, we find that the grandest legal drama of our time is being written in absolute silence 250,000 miles away. It is a conflict not of armies, but of legal frameworks, where the ancient principles of property and presence are being reinvented for the cosmic age. For a generation that remembers the structured certainty of the mid-20th century, the modern rush to the moon reveals a fascinating legal paradox, a race to claim ownership without ever violating the law. To understand this quiet battle for celestial real estate, we must first look back to the foundation of all cosmic law, a grand international document known as the Outer Space Treaty of 1967. Signed during the height of the Cold War, this treaty established the beautiful principle of res communis, a Latin legal term meaning a common pasture or a global resource that belongs to all of humanity and cannot be claimed by any single nation. Under this agreement, no country can plant a flag on the moon and declare it sovereign territory. The grey dirt cannot be annexed like a new province or a colony of old. For 50 years, this treaty maintained a peaceful, untouched sanctuary in the night sky. But as modern technology brings the lunar surface within our reach, Brilliant legal minds have uncovered a massive golden loophole within the ancient text. While a nation cannot own the lunar land itself, the treaty says absolutely nothing about who owns the materials you extract from that land. This subtle distinction has birthed a revolutionary legal mechanism pioneered by the United States known as the Artemis Accords. To bypass the restrictions of the 1967 treaty, these modern accords introduce a highly sophisticated diplomatic concept known as a safety zone. To the layman, a safety zone can be understood as a temporary, invisible perimeter fence set up around an active mining site or a scientific outpost. Under this framework, if an American company or a NASA lander arrives at a specific location, first to harvest water ice or drill for valuable minerals, they have the right to declare a protective buffer zone around their machinery. They argue that this zone is necessary to prevent harmful interference, a technical phrase meaning the dangerous disruption caused by another country landing too close, which could spray destructive rocket exhaust over sensitive equipment or disrupt delicate communications. While this concept sounds completely reasonable on paper, its practical application creates what political scientists call de facto sovereignty. This is a profound legal phrase, meaning a state of affairs that exists in actual reality, even if it is not formally recognized by an official treaty. By establishing a safety zone that bars other nations from entering or operating within a specific perimeter, the country that arrives first effectively gains exclusive control over that piece of real estate for as long as their machinery operates. They do not own the land under the law, but because no one else can legally enter it, they possess total, undisputed mastery over its treasures. It is a quiet, bloodless evolution of the ancient law of the frontier, the rule of the first finder. This brings us to the immense strategic importance of the first mover advantage, the absolute geopolitical leverage gained by the nation that manages to plant its boots and robots on the ground before anyone else. On a world as vast as the moon, one might think there is plenty of room for everyone. But as we have learned from the delicate mappings of modern satellites, the prime real estate on the lunar surface is incredibly scarce. The true treasures of the cosmos, the elevated peaks of eternal light that offer infinite solar energy, and the deep freezing crater rims that hold billions of tons of water ice are no larger than a few square miles across, clustered tightly at the absolute bottom of the lunar globe. There are only a handful of these perfect locations, and under the rules of the safety zones, whoever touches them first wins the right to lock the gate. The nation that establishes the initial infrastructure will dictate the economic rules of the next century. They will control the water, they will control the power grids, and they will set the standards for how celestial commerce is conducted. Latecomers will find themselves relegated to the barren, unprofitable deserts, forced to buy resources from those who had the vision and the stamina to arrive first. It is a quiet, high-stakes game of cosmic chess, where the board is being claimed space by space in the utter tranquility of the deep dark. When we look at the modern race to the moon, it is easy to view it merely as an outward journey, a spectacular display of thunderous rockets escaping our atmosphere. Yet for the nations pouring their hearts and treasuries into the deep void, the true destination is not the silver dust of the moon. The real journey is inward. It is a deliberate, high-stakes catalyst designed to fundamentally upgrade a country's domestic industrial landscape and awaken the deep, sleeping giant of national pride. For a generation of Western onlookers who remember the industrial booms of the mid-20th century, this aspect of the space race carries a familiar, comforting truth. To build a machine capable of surviving the cosmos, you must first perfect the factories on the ground. To understand this domestic transformation, we must look at a profound economic phenomenon, known to strategic planners as technological spillover, the natural downstream river of innovation where advanced techniques developed for the extreme frontier trickle down into civilian factories, revolutionizing everyday manufacturing. A space program is the ultimate upstream mountain spring. You cannot reach the moon using ordinary off-the-shelf components. The vacuum of space is a brutal, unforgiving master that demands a total rewrite of industrial capabilities. By forcing local scientists and domestic factories to solve the impossible problems of space travel, a nation forces its entire economy to mature, escaping the frustrating limitations of low-value assembly lines and entering the Premier League of global engineering. Consider the microscopic world of radiation-hardened microelectronics, highly specialized, integrated circuits engineered to withstand the invisible high-energy bombardment of cosmic rays without glitching or melting down. In our comfortable earthly environment, our thick atmosphere shields our computers from this deep space radiation. But out in the void, a standard microchip would fail within minutes. To build these hardened brains for lunar rovers, a nation must cultivate a pristine domestic semiconductor industry. They must master the art of etching circuitry onto silicon at the scale of mere nanometers, microscopic measurements so incredibly small that millions of transistors can fit on the head of a single pin. Once a country masters this delicate art for its space probes, that very same technological know-how flows directly into their civilian sectors. Suddenly, domestic factories gain the capability to produce ultra-reliable medical equipment, sophisticated automotive computers, and advanced automation systems for local power grids. The pursuit of the moon turns a developing economy into a high-tech powerhouse. We see this same upgrading force within advanced structural metallurgy, the complex science of manipulating the atomic bonds of metals to create new alloys that are incredibly light yet possess immense tensile strength. A rocket traveling to the moon must endure the violent, teeth-chattering vibrations of launch, followed by the terrifying thermal cycles of space, where temperatures swing from blistering heat to hundreds of degrees below zero in a matter of minutes. To survive this, domestic steel mills and metal foundries must evolve. They learn to forge exotic titanium aluminum matrices and advanced carbon fiber composites materials that are stronger than industrial steel but weigh less than a feather. Once these materials are perfected for the hull of a lunar lander, they find a natural home back on Earth, upgrading the civilian manufacturing chain. They are used to build safer, more fuel-efficient commercial aircraft, stronger bridge supports, and durable deep-sea drilling equipment. The nation effectively escapes the middle-income trap, the economic dead end, where a country can only compete by offering cheap labor, by transforming its workforce into master craftsmen of high-value technology. Alongside this mechanical upgrade sits an equally powerful invisible force, the cultivation of autonomous cybernetics. This is the branch of computer science focused on creating self-thinking artificial intelligence systems capable of navigating treacherous terrain without any human intervention. Because the vast distance between the Earth and the Moon creates a noticeable communication delay, a lunar rover cannot be driven with a joystick from a control room on Earth. It must see the rocks, recognize the hazards, and make its own split-second decisions to survive. By developing these autonomous eyes and brains for the lunar South Pole, a nation builds the foundational architecture for the future of its domestic automation. These same algorithms are soon deployed in automated cargo ports, precision agriculture drones, and smart manufacturing robots that can run entire factories in perfect silence through the night. Yet beneath all the wires, silicon chips, and exotic metals lies the most potent fuel of all the deep transcendent currency of national prestige. For any country seeing their flag painted on the side of a roaring rocket, watching their homegrown machinery land flawlessly on a distant world provides a profound psychological awakening. It is a declaration to the world, and more importantly, to themselves, that they are no longer mere spectators in human history, they are the authors of the future. This shared pride acts as an invisible social cement, unifying a population and inspiring a new generation of young minds. Bright students who might otherwise choose comfortable careers in finance or software engineering are drawn back to the heavy, noble sciences of physics, chemistry, and mechanical engineering. They look up at the night sky and realize that their nation's destiny is limited only by their collective imagination. In the quiet watch of the night, when the heavy demands of geopolitics and earthly rivalries dissolve into the shadows, our minds can trace the ancient patterns of human strategy. Throughout history, the master tactician has always sought one fundamental advantage: the high ground. From the stone fortresses built upon European crags to the radar towers perched upon Pacific cliffs, whoever holds the summit commands the valley below. Today, as we lift our eyes to the silver light outside our windows, we find that the definition of the high ground has broken free from the mountaintops. It has ascended into the absolute silence of cislunar space. To the modern strategist, cislunar space is a term of profound importance, a beautiful scientific phrase that simply describes the vast velvet ocean of emptiness stretching between the upper edge of Earth's atmosphere and the far-flung orbit of the Moon. For generations, this region was regarded as a lonely vacuum, a quiet highway through which Apollo capsules traveled. But in this new century, military minds view it as the ultimate maritime choke point, the grand thoroughfare through which all future traffic to the stars must pass. To control cislunar space is to control the gateway to the next era of human civilization. The military value of this domain lies in the unique physics of its deep vantage point. In the realm of defense, scientists talk of the gravity well, a physical concept describing how a massive body like the Earth pulls everything toward its center with an invisible heavy grip. Trying to launch a missile or a telescope from the bottom of this well up into deep space requires an extraordinary, punishing amount of energy. But looking down from the top is a completely different story. A nation that positions its monitoring systems in cislunar space can observe the entire planet and every satellite circling it with absolute clarity, using only a fraction of the energy required by ground-based systems. Within this vast celestial ocean lie unique positions known as Lagrange points, gravitational sweet spots, where the pulling forces of the Earth and the Moon balance out perfectly with the momentum of a satellite. To the layman, a Lagrange point can be understood as a quiet, cosmic eddy, a peaceful harbor in the middle of a rushing river, where a spacecraft can park itself and float forever, consuming virtually no fuel at all. From these invisible lookout towers, an advanced tracking platform can peer down into the crowded lanes of low Earth orbit, the narrow band, where our weather communication and military satellites glide. An adversary operating from these dark outposts can track every move of a nation's orbital infrastructure, remaining completely hidden in the immense glare of deep space. Furthermore, cislunar space offers a dangerous advantage known as orbital asymmetry, an engineering phrase meaning that it is far easier to slip down from a high orbit to a low orbit than it is to climb back up. A spacecraft hiding in the deep lunar shadows could easily alter its path, descending toward Earth with immense speed, catching ground-based tracking systems completely by surprise. The Moon itself becomes the ultimate stationary aircraft carrier, a natural, unshakable fortress from which a nation can deploy its eyes and ears to oversee the globe. It is a quiet, high-stakes game of hide-and-seek, played out against a canvas of cold, brilliant stars. While many nations now gaze toward these rich lunar shores, the grand narrative of this new century ultimately narrows to a profound clash of two giants. The United States and China are moving toward an inevitable rendezvous in the silver dust. To see who truly leads this quiet march, we must look into the shadows and carefully balance their budgets, their machinery, and their competing visions for tomorrow. The cosmic calendar has suddenly accelerated as we look at the strategic playbooks of the world's two greatest space powers. From our vantage point in mid-2026, the long-term abstract promises of the past decade have dissolved into immediate hard-engineered deadlines. The modern arena is no longer defined by vague aspirations. It is governed by rigid flight manifests, narrow launch windows, and shifting geopolitical realities. Just a few months ago, in April of 2026, the world witnessed the triumphant completion of NASA's Artemis II mission. For 10 magnificent days, a courageous crew of 4 slipped behind the lunar horizon, becoming the first human beings to look down upon the crater-scarred far side of the Moon with their own eyes in over 50 years. It was a spectacular confirmation that the long hibernation of the West had officially ended, yet the path forward has proven to be a dynamic, ever-changing landscape of engineering pragmatism. The American strategy, orchestrated through the sprawling architecture of the Artemis program, underwent a profound and calculated realignment in the spring of 2026, in a move that highlights the immense complexity of modern deep space transport. NASA adjusted its immediate sequence to ensure absolute safety and operational readiness. The upcoming milestone, Artemis III, is now targeted for the latter half of 2027. Rather than risking a direct landing on the challenging lunar terrain on the very first try, this mission has been redesignated as a monumental crewed demonstration in low Earth orbit. A seasoned crew of 4 astronauts will blast into the heavens aboard the Space Launch System rocket, tasked with mastering the intricate high-stakes choreography of rendezvous and docking with the massive privately developed human landing systems currently being fabricated by commercial titans. This flight will serve as the ultimate crucible for the life support networks and interoperability software that will sustain humans in the deep dark. This prudent step sets the stage for the true crown jewel of the American return, Artemis IV, scheduled to roar off the launch pads in the early months of 2028. This historic expedition will carry the heavy mantle of the first crewed lunar landing since the departure of Apollo 17 in 1972. 2 brave pioneers will step onto the treacherous, ice-rich landscape of the lunar South Pole, transforming a half-century of waiting into a brilliant new dawn. They will be followed in short order by Artemis V in the closing months of 2028, an ambitious mission designed to deploy heavy mobility infrastructure, including advanced rovers, and begin the construction of a permanent habitat on the Silver Shore. Yet while Washington refines its blueprints with a focus on human operations and orbital tests, the architects in Beijing are marching to the steady, unyielding beat of a completely different drum. The Chinese lunar exploration program operates with a rigid linear progression that treats robotic machines as the essential vanguard for human boots. The next grand movement in this Eastern Symphony is scheduled to unfold in the final months of this very year, 2026, with the launch of the Chang'e 7 expedition. Lifted by the thunderous power of a Long March 5 heavy rocket, this massive robotic armada will descend directly upon the illuminated rim of the Shackleton crater at the lunar South Pole. This mission will mark the debut of the extraordinary spider-like flying probe designed to leap into the permanently shadowed abysses, braving temperatures colder than deep space, to confirm the exact purity and depth of the ancient water ice. Once this critical resource data is secured, the Eastern campaign will seamlessly transition to its next grand milestone, Chang'e 8, currently scheduled for launch around 2029. Targeting a flat plateau known as Leibniz Beta, this mission will transition the program from mere exploration to active industrial preparation. The lander will carry highly sophisticated automated systems designed to test in situ resource utilization, the art of using local materials rather than hauling supplies from Earth, including an extraordinary experiment that will attempt to three-dimensionally print structural bricks out of the raw lunar soil. All of this robotic groundwork is engineered to converge into a historic crescendo. China has formally committed to executing its first crewed lunar landing before 2030. This bold expedition will utilize two independent launches of their newly developed Long March 10 rockets, sending a crewed capsule and a landing module to link up in lunar orbit before placing two Chinese astronauts into the pristine polar dust. In the race to the moon, the nominal budget the headline figure reported in the morning paper is often an illusion that masks the true operational velocity of a nation. To understand the current theater of operations, we must first look at the raw commitments. The United States, through the National Aeronautics and Space Administration, currently operates with a total annual budget hovering around $25 billion. Within that vast framework, the Artemis program, the high-stakes flagship effort to return humans to the lunar surface, commands a significant and dedicated portion, consistently averaging between $7 and $9 billion every fiscal year. It is a massive concentrated investment, visible, transparent, and debated openly in the halls of Congress. In contrast, the architects in Beijing operate with what we might call strategic ambiguity. The Chinese National Space Administration does not publish a neat line-item budget that you or I could audit with ease. However, rigorous intelligence analysis from outside observers estimates their total annual investment in the space sector to be between $12 and $15 billion. Of that figure, the Chinese lunar exploration program, the grand multi-phase Chang'e endeavor, is estimated to consume roughly $3 to $4 billion per year. At first glance, one might assume the United States possesses an overwhelming financial advantage, outspending the East by a margin of 2 to 1. But this is where we must apply the lens of purchasing power parity, a critical economic concept that every seasoned executive understands. Purchasing power parity measures the real-world value of a currency based on what it can actually acquire within a specific national economy, rather than its fluctuating value on international currency exchanges. When applied to the brutal high-tech world of rocket manufacturing, purchasing power parity acts as a profound financial equalizer. In the West, our space budget is paid in American dollars, which must contend with high labor costs, unionized workforces, stringent environmental compliance, and the expensive overhead of a mature, regulatory-heavy aerospace industry. A significant percentage of every dollar spent by NASA is absorbed by the administrative machinery, legal compliance, and the premium cost of highly skilled engineering labor in a competitive Western market. Now consider the economic reality in China. Their industrial ecosystem is vertically integrated, meaning the state controls everything, from the steel mills to the semiconductor fabrication plants. They do not face the same cost structures for labor raw materials or administrative overhead. An engineer in Beijing, despite being of equal caliber and dedication to a counterpart in Houston or Huntsville, is paid a salary that reflects the local cost of living. When you factor in this disparity, $1 billion of purchasing power in China can effectively buy 3 to 4 times the industrial output, raw materials, and engineering hours as $1 billion spent within the American economy. In practical terms, this means that while the American ledger shows a higher nominal spend, the actual bang for the buck on the factory floor is much closer than the headline numbers suggest. When China pours $3 to $4 billion into their Lunar program, they are often securing the equivalent industrial and engineering effort that would cost the United States well over $10 billion to replicate. They are effectively neutralizing the American financial advantage through sheer, calculated operational efficiency. This is the hidden engine of the lunar race. It is not just about who has the largest treasury. It is about who extracts the most progress from every single unit of currency. It is a lesson that history has taught us time and again. The winner is not always the one with the deepest pockets, but the one with the most efficient furnace. When we look at the mechanical heart of any truly great enterprise, we inevitably recognize a classic divergence in engineering philosophy. It is the age-old choice between the radical disruptive breakthrough that risks everything to completely rewrite the rules of the game and the steady, iterative pragmatism that relies on proven principles to guarantee a predictable result. In this modern campaign for the silver horizons of the moon, this philosophical divide is perfectly embodied by the 2 towering launch vehicles designed to carry human ambitions into the deep dark, the American Starship and the Chinese Long March 10. It is a compelling study in technological risk management that any seasoned professional can appreciate. Let us first observe the American contender, the colossal Starship architecture forged in the high-stakes, rapid-fire crucible of private enterprise. This vehicle represents a magnificent, borderline terrifying leap in aerospace design. Unlike any rocket that has ever graced a launch pad, Starship is engineered to be completely and rapidly reusable, a feat that requires both the massive booster stage and the upper spacecraft to perform vertical landings back on Earth using autonomous precision. It is propelled by a roaring cluster of over 30 liquid methane and liquid oxygen engines, a highly advanced propellant combination that offers immense theoretical efficiency but requires managing extreme pressures and super-chilled temperatures. However, the true audacity and the inherent danger of the American paradigm lies in its orbital refueling bottleneck. Because the vehicle is too massive to carry all its fuel out of Earth's heavy gravity well, Starship must park in low orbit and be replenished by a train of multiple separate tanker flights. This requires the automated transfer of hundreds of tons of volatile cryogenic liquid propellant in the weightless void of space, a dangerous, unproven maneuver that serves as a single point of failure for the entire Western timeline. Now let us turn our attention to the Eastern challenger, the Long March 10. If Starship is a disruptive high-risk Silicon Valley gamble brought to life in gleaming steel, the Long March 10 is a masterfully refined industrial locomotive built on the absolute certainty of traditional physics and decades of operational data. The strategic planners in Beijing have explicitly rejected the chaotic trial-by-fire development cycle of their rivals. Instead, they have designed a highly practical three-stage heavy rocket that utilizes conventional liquid hydrogen, liquid oxygen, and refined kerosene propellants. There are no radical, unproven refueling gymnastics required in low Earth orbit. Instead, China's architecture relies on a dual-launch strategy that is as elegant as it is straightforward. One Long March 10 rocket will lift the crew capsule into space, while a second identical vehicle will launch the lunar lander. The two spacecraft will perform a standard rendezvous and docking in lunar orbit, a mechanical handshake that human space programs have successfully executed for over half a century. It is a conservative, incremental approach that sacrifices the long-term dream of total reusability in exchange for immediate, unshakable mission reliability. When we weigh these two technological philosophies on the engineering scale, the contrast is stark. America is betting its immediate lunar return on a magnificent, dangerous revolution, pushing the absolute boundaries of what modern materials and computing can achieve. If it succeeds, it will grant the West an unparalleled logistical dominance across the solar system. China, conversely, is executing a disciplined, practical march. They are not waiting for the deep future to invent itself. They are using the refined, reliable tools of today to ensure their astronauts hit the gray polar dust before the decade closes. It is a classic race between the tortoise of absolute certainty and the hare of radical innovation. When we strip away the blinding flash of rocket exhaust and the sophisticated mathematics of orbital trajectories, we are left with the truest engine of any great human epoch, the institutional architecture of the society that built it. Every massive historical endeavor, from the grand Roman aqueducts to the transcontinental railroads of our own western frontier, was ultimately a reflection of the political and economic systems that financed and directed them. As we watch the modern campaign for the silver horizons of the moon unfold in this 21st century, we are witnessing a profound, silent clash of two completely opposing ideological titans. It is a struggle that goes far beyond a simple race between Washington and Beijing. It is a masterclass in institutional risk management, pitting the chaotic competitive brilliance of private capitalism against the disciplined, monolithic certainty of state capitalism. For anyone who has spent a lifetime navigating the structures of Western commerce, this institutional duel is perhaps the most fascinating chapter of the entire saga. Let us first examine the Western paradigm, an architecture that has undergone a radical historic transformation over the past 2 decades. During the original space race of the 1960s, the American approach was entirely state-directed, with the federal government acting as the sole funder, architect, and operator of every piece of hardware. Today, however, Washington has pioneered an entirely new philosophy based on the fierce dynamics of the free market. Under this modern system, the state has stepped back from its role as a master builder, choosing instead to act as a primary customer. Through the utilization of fixed-price, milestone-based procurement contracts, the National Aeronautics and Space Administration no longer owns the rockets or the landers. It simply buys a ticket on transport systems designed, built, and operated by private commercial entities. The virtues of this private capitalist model are undeniable and deeply rooted in our Western traditions of entrepreneurial initiative. By unleashing the forces of corporate competition, the American model fosters a culture of explosive, disruptive innovation. Private aerospace firms driven by the relentless discipline of venture capital and fiduciary responsibility to their shareholders, are forced to achieve operational efficiencies that would be unthinkable within a traditional government bureaucracy. This system rewards radical risk-taking, leading to breakthroughs like rapidly reusable booster stages and entirely new methods of automated manufacturing. However, this brilliant free market engine carries a significant and vulnerable structural bottleneck. It is entirely exposed to the turbulent winds of democratic political cycles. Every 4 or 8 years, a shift in the executive branch or a change in the balance of power within Congress can bring a completely new set of priorities. Budgets can be reallocated, programs can be cancelled, and strategic goals can be rewritten overnight, causing a form of institutional whiplash that can stall progress and frustrate even the most dedicated engineers. Now let us turn our gaze to the Eastern Challenger, where the concept of state capitalism has been elevated to an art form of absolute strategic discipline. In Beijing, there are no independent commercial titans competing for dominance, no volatile venture capital markets to appease, and no quarterly earnings reports to dictate the pace of development. The entire Chinese aerospace apparatus operates as a singular unified instrument of the state, directed from the very top through massive state-owned enterprises like the China Aerospace Science and Technology Corporation. This model completely eliminates the internal friction that defines the Western marketplace. There are no redundant designs, no wasteful corporate legal battles over patents, and no public debates over the allocation of national resources. The supreme weapon of this state capitalist framework is its absolute immunity to short-term political shifts. The strategic planners of the East do not operate on the timeline of the next election cycle. They chart their course by the steady, unyielding cadence of multi-decade grand strategies and 5-year plans. When a goal is set, such as placing automated rovers on the lunar far side or establishing a robotic research station at the southern pole, the entire industrial might of the nation is mobilized behind it with absolute consistency. Funding remains guaranteed for decades, allowing scientists and engineers to work with a level of long-term structural certainty that Western managers can only look upon with envy. Yet this monolithic approach is not without its own deep institutional risks. By eliminating the chaotic crucible of market competition, state capitalism can easily fall victim to the dangers of bureaucratic inertia. Without the pressure of commercial competitors, innovation can become rigidly incremental, and the system can become slow to adapt when faced with unexpected technological failures. When we weigh these two grand ideologies on the scale of history, we see a beautiful high-stakes paradox. America is betting its lunar future on the brilliant, erratic flash of individual genius and market competition, trusting that the agility of private enterprise can overcome the structural instability of its political system. China, conversely, is relying on the heavy, predictable grinding of a centralized command economy, betting that patient discipline and absolute continuity will ultimately wear down and outlast their Western rivals. It is a classic confrontation between the agile hawk and the unyielding tortoise, played out against the vast canvas of the deep cosmos. As we look back across the long landscape of global statecraft, we inevitably recognize a fundamental law of history. No empire, no matter how vast its treasury or how advanced its factories, can hold a new frontier entirely alone. True mastery of an untamed territory requires a network of deep alliances, a coalition of shared values, and integrated supply chains that can distribute the massive financial burdens and provide absolute geopolitical legitimacy. As we observe the modern race for the silver horizons of the moon, this ancient principle has broken free from our earthly oceans and ascended into the deep cosmos. We are no longer witnessing a simple duel between isolated superpowers. Instead, the 21st century has given birth to a grand war of cosmic coalitions, a deep diplomatic chess game that splits the international community into two distinct competing spheres of influence: the American-led Artemis Accords and the Chinese-led International Lunar Research Station bloc, with the proud, bruised empire of Russia acting as a critical pivot point in the strategic calculus. The Western Front, the grand coalition of the Artemis Accords. Let us first examine the Western Front, orchestrated by Washington through a masterful diplomatic framework known as the Artemis Accords. Grounded in our shared traditions of free market capitalism, democratic transparency, and the rule of law, these accords represent the largest space coalition in human history, drawing in dozens of nations from every corner of the civilized world. This is not merely a collection of signatures on a page, it is a highly sophisticated mechanism of interoperability. By establishing unified standards for everything from docking mechanisms to communication frequencies, the United States is building a vast, integrated industrial ecosystem where a component forged in a British foundry or a software package written in a Japanese laboratory can plug seamlessly into an American rocket. The strategic beauty of the Artemis framework lies in its soft power appeal. It offers traditional Western allies and emerging tech-driven nations a coveted seat at the premier table of cosmic commerce, allowing them to upgrade their domestic tech sectors without having to build a native heavy-lift rocket program from scratch. By standardizing the concepts of open scientific data and the utilization of local resources under the protective umbrella of safety zones, the Accords are quietly setting the legal and commercial rules of the road for the next century, ensuring that the Free World Alliance maintains structural dominance over the high ground of space. The Eastern Axis, the rise of the ILRS bloc. Beijing, however, did not stand by passively while the West consolidated its diplomatic lines. Recognizing that the Artemis Accords were designed to reinforce Western hegemony, the strategic planners of the East launched their own powerful counter-strategy, the International Lunar Research Station. This is a bold, state-centric vision that rejects the Western model of commercial privatization in favor of a heavy government-to-government infrastructure network. Rather than relying on the volatile dynamics of corporate markets, the Eastern Bloc offers its partners the unyielding long-term predictability of state funding and centralized command. The diplomatic calculus behind this Eastern Axis is remarkably pragmatic. Beijing has deliberately positioned its coalition as an open anti-hegemonic alternative, actively courting nations that feel excluded by Western export controls or those that prefer a state-directed model of industrial development. By offering access to their massive Long March rockets and their highly successful Chang'e robotic landing data, China is assembling a formidable counter-coalition that stretches across Eurasia, Africa, and parts of Latin America. It is a deliberate effort to create a parallel cosmic economy, complete with its own regulatory frameworks, its own technology standards, and its own vision of how the wealth of the moon should be distributed. The Russian card legacy, power, and strategic interdependence. And then we must analyze the most complex and fascinating variable in this entire geopolitical equation, the Russian Federation. To any observer who understands the deep history of the 20th century, Russia possesses an unparalleled sacred pedigree in the cosmic arena. They are the proud descendants of the Soviet space program, the empire that shook the West to its core by launching Sputnik, putting Yuri Gagarin into orbit, and mastering the brutal engineering of long-duration space stations. Even in the modern era, Russian engineers possess a deep tribal knowledge of rocket propulsion, life support systems, and heavy metal fabrication that few nations can match. Yet the harsh realities of modern history and severe economic constraints have prevented Moscow from executing a solitary frontline lunar campaign. This vulnerability has forced a profound strategic realignment. By throwing its immense historical weight and technical heritage behind China's International Lunar Research Station, Russia has assumed the role of the ultimate junior partner to Beijing. It is a marriage of immense pragmatic convenience. For China, the alliance with Russia provides an instant infusion of veteran engineering expertise, decades of flight-proven technology, and a powerful layer of historical legitimacy that transforms their program from a unilateral national project into a grand, multinational alliance. For Moscow, the partnership offers a vital lifeline, allowing its proud space agency, Roscosmos, to remain relevant on the absolute cutting edge of human exploration, funded by the deep pockets of the Eastern Giant. This combined front creates a deeply formidable adversary, fusing Russia's rugged Cold War engineering stamina with China's limitless manufacturing velocity. As you reflect tonight upon this grand, quiet clash of global coalitions and the shifting balances of celestial power, let the heavy complexities of international statecraft begin to drift away from your thoughts. The fierce debates of diplomats, the strategic calculations of generals, and the competing treaties of earthly empires belong to a daylight world of noise and friction that has no power over the peaceful sanctuary of this room. As the world observes the grand lunar chessboard in this pivotal summer of 2026, the race to command the silver horizons has narrowed to a profound clash of operational styles. Stripping away the public relations glare reveals that the two superpowers are driving toward the same destination, using completely opposite mechanical philosophies. One behaves like a high-performance racing car, while the other moves like a heavy diesel locomotive. The American-led Artemis program operates precisely like a cutting-edge Formula One racing car. It is a magnificent testament to raw technological audacity, custom-built from exotic materials and propelled by the explosive, disruptive energy of private enterprise. The triumphant completion of the Artemis II flight in April of 2026 provided an undeniable confirmation that the West still possesses the unique foundational grit required to send humans back into the deep void. Yet just like a fine-tuned racing machine, this architecture is incredibly fragile and highly sensitive to operational friction. The Western strategy relies on a radical, unproven refueling bottleneck in low orbit, a logistical maneuver that resembles trying to change tires at 200 miles per hour in pitch darkness. Because the program relies on a decentralized web of commercial contractors and remains exposed to shifting political winds, the timeline has begun to experience significant whiplash. With Artemis III recently adjusted to an orbital dress rehearsal in 2027 and the actual landing boots on the ground delayed until 2028, this brilliant racing car is spending too much precious time idling in the pit lane while mechanics tweak the engine. Across the track, the Eastern Challenger operates with the quiet, unyielding rhythm of a massive diesel locomotive. It lacks the sleek, aerodynamic beauty of a sports car, and it certainly does not make headlines for radical disruptive engineering leaps. Instead, its iron wheels grind forward on a perfectly straight track, built on proven physics and decades of reliable data. Backed by the immense practical advantage of domestic purchasing power parity, every unit of capital spent on this freight train stretches 3 to 4 times further than a Western dollar. Furthermore, this locomotive is completely insulated from changing drivers or shifting political seasons. Its route was mapped out years ago in rigid multi-decade blueprints that do not fluctuate with an election calendar. While the West tinkers with its revolutionary propulsion systems, the Eastern train is pulling into its scheduled stations with absolute clockwork predictability. The Chang'e 7 robotic armada is already sitting on the tracks, cleared for departure in the closing months of this very year, 2026, to secure the ice-rich real estate of the Southern Pole. It will be followed immediately by Chang'e 8, laying down the literal bricks for a permanent outpost before the decade closes. So when we look at the leaderboard today, who is truly winning the race? If the prize is awarded for raw engineering genius and the long-term depth of a global coalition, the Western racing car still holds the strategic high ground. The Artemis Accords have built a diplomatic fortress that will likely dominate the cosmic economy of the next century. But if the scoreboard is judged by strict timeline discipline, execution certainty, and near-term operational velocity, the diesel locomotive has quietly stolen the lead. China has successfully stripped the chaos out of a wild frontier, transforming a grand cosmic adventure into a predictable manufacturing pipeline. They are not waiting for the future to invent itself. They are using the heavy, reliable tools of today to ensure they lock the polar gates first. As these compelling strategic realities settle into your thoughts tonight, the fierce roar of the engines and the heavy clattering of the tracks begin to fade into the evening stillness. The complex ledgers, the race for the Southern Pole, and the frantic ambitions of competing empires belong to a daylight world of action and friction that cannot reach the serene sanctuary of this room. Out there in the vast, unbothered dark, the moon continues its ancient serene journey, casting its soft, impartial silver light over our turning world. The ancient grey deserts do not take. They remain locked in a state of perfect eternal peace beneath a sea of cold, brilliant stars. Feel the steady, comforting rhythm of your own breathing, calm and natural, and allow your mind to slide gently into the deep, restorative tranquility of a long and restful sleep.